Welcome. I'm Ganyan Park, and today I'm going to present our research on training device subnetworks with contrastive weight pruning. Our aim is to mitigate sparse correlation or short learning problem. Here, we diagnose this problem as architecture design issue, where if there are any available channel connected to bias attribute, it may bias the representations. Our idea is to prune the weight on bias attributes so it may debias the representations. We have two observations, where first one reveals the limitations of existing pruning, and second one is about how bias completing samples may overcome these limitations. We designed a new neural pruning algorithm called DCWP, and we demonstrate that the proposed method outperforms other debiasing methods. So first, we start with a theoretical example which simulates sparse correlation in a simple linear setting. Consider we have a invariant and sparse features. For sparse features, we assume that they are aligned well with the target variable with high probability PE. In test environment, they becomes completely random. Based on this environment, we introduce our pruning parameters pi. This pi simply implies the probability of preserving weight on each features. So for example, for a given pi, we define a Bernoulli distribution and sample a weight mask M. If this mask M equals 0, the corresponding feature or weight is masked out. And our goal is to optimize pi in a way to guarantee generalization. Intuitively, this means that we have to increase pi sparse to prune out sparse features or weight with a high probability. So for limit, we first observed that the standard pruning algorithm failed to close the generalization gap. In detail, although we optimize pies in a biased training environment, it does not guarantee the generalization of subnetworks in a debiased test environment. This is because the increase of pi sparse contributes to the minimization of training overbound. From the optimization perspective, there is no reason to prune out these sparse features if a bias probability P is high. So, in order to mitigate this problem, we design a new environment where we can augment bias completing samples. In detail, we assume a new distribution P debias and mix this one with a existing biased distribution. It turns out that this mixture of debiased distribution can close the generalization gap. Specifically, as we sample more from the true debiasing distribution, the gap between training and test bound decreases. If we set the mixture coefficient to a optimal value, the mixture distribution is perfectly debiased, and the training bound becomes exactly equal to the test bound. This observation provides us important clues on pruning debiased subnetworks. So, we first have to approximate the unknown P debias and modify the sampling strategy to simulate the P mix. So based on these clues, we design a new neural pruning algorithm called Debiased Contrastive Weight Pruning, or DCWP. We first pre-train a network with a standard cross entropy loss. Based on this biased network, we apply a neural pruning with our objective denoted in number 1. Our objective includes a uniform sparsity constraint and debiasing loss. The uniform sparsity constraint is implemented with a error loss of pruning parameters. For a debiasing loss, we first mine bias completing samples included in training set. Then, we oversample these identified samples to simulate the mixture distribution. We have compared the debiasing method with 4 datasets, namely CMNIST, SALPAR, BFFHQ, and Celebay. Each dataset is biased with a specific attribute, such as color, Gaussian type, or gender. Our tables show that the proposed neural pruning outperforms state-of-the-art device method. Moreover, we conducted an ablation study to quantify the impact of neural pruning on bias robustness. As shown in table on the left, the neural pruning debiased representations to a significant extent. Moreover, we observed that the proposed pruning does not require weight reset. All we have to do is pre-train a network, prune out sparse weight, and resume the training. And from our sensitivity analysis, we have observed that the unbiased test accuracy actually increases as more weights are pruned out. This implies that the pre-trained bias networks contain a lot of redundant bias weight or features. And we further figure out that the proposed pruning is reasonably tolerant to a high level of sparsity. For example, we vary the degree of uniform sparsity constraint and control the pruning ratio. While we have pruned out almost 90 to 95% of weights, the pruned out subnetworks record high unbiased accuracy. And we further analyzed the robustness of neural pruning against the precision of identified bias completing samples. For this comparison, we intentionally limit the precision and recall of identified bias completing samples. Even with this inaccurate process of bias conflicting samples, the proposed framework performed reasonably well. And here, we visualize the latent representations before and after pruning. While the biased representations are aligned with bias level, the pruned representations turns out to be well aligned with the target label, and the fine-tuning stage further improves the alignment. And here's the summary. We present a novel functional subnetwork proving method for the OOD generalization. We provided theoretical insight and empirical evidence that the minority samples play an important role for discovering the optimal unbiased subnetworks. The proposed method is memory efficient and potentially compatible with many other device methods. For more details, please visit our poster session or archive website. Thank you.